Hello everyone. Today I am going to talk about the root locus, which is very important topic of the third unit of the control system. So this is the basic concept of the contents of the today's lecture. First of all, I'll discuss the introduction. That means what is root locus, what is the need of root locus, who invented this root locus, why this came into the picture, right? So then what is the concept of the root locus, then what are the angle and the magnitude condition which are related to the root locus, and then what are the different rules which we can use to construct the root locus, and in the last I'll discuss some example related to the root locus. So starting with the introduction, as we all know that the stability of any closed loop system can be determined from the location of poles of the characteristic equation, right? That means roots of the characteristic equation, that is the location of poles, will determine the stability of any closed loop system. And the nature of the transient response, since the nature of the transient response is closely related with the location of closed loop poles, so it is very important to know how these poles are moving in the S-plane. So it will, whenever a particular parameter is varying in the system, so it is advantageous to know how we can determine the movement of pole in S-plane, because it will help us to design any closed loop system, right? So we can say that the root locus is the locus of the roots of the characteristic equation of the closed loop system whenever a particular parameter, usually the gain k, is varying from 0 to infinity. So this technique was introduced by W.R. Evans in 1948. So we can say that the root locus is a graphical method in which the different roots can be sketched in S-plane, that so that we can come to know the movement of the poles in the S-plane, right? And these are the advantages of the root locus method. This is the powerful method for the analysis purpose and the design for the stability of any system and for the determining the transient response of any control system. It basically gives us the information about the absolute stability as well as the relative stability of any system. It also determines the range of the stability and the range of the instability, right, and the conditions which will cause the system to break into the oscillations. And we can use this root locus method to solve higher order algebraic equations. Now let's talk about the basic concept of the root locus. See, as we know that the general characteristic equation of any closed loop system is 1 plus GSHS is equals to 0, right? Let's say this is the block diagram of any system in which this variable k, or you can say gain k, is varying. Okay, this is the CS is the output of this system, and let's say this is the system with feedback HS, and this is RS, and this is the negative feedback system. So this characteristic equation here, GS will be equal to, since I have introduced this gain k, which is a variable parameter in the forward path, so I can write this GS as k into G dash S, and now the characteristic equation for this system will be 1 plus k into G dash S into HS. And now let's say it is a unity feedback system and HS is equals to 1. Now 1 plus k G dash S is equals to 0 will be the new characteristic equation. Now if I vary this value of k, right, so for each separate value of k, I'll get separate set of the poles of the closed loop system, separate roots of S, right, for closed loop system. So basically if I vary this gain k from minus infinity to plus infinity, I'll get different values of S. We can say different roots of the closed loop system. Now, see, if I say that, look, here I am saying that I am varying k from minus infinity to infinity, right? So here we can break this variation of k from minus infinity to 0 and 0 to infinity. Okay, so this is known as, when the parameter is varying from 0 to infinity, then that is known as direct root locus method. And if any parameter or gain k is varied from minus infinity to 0, then it is known as inverse root locus method. So in general terms, we generally for root locus we use direct root locus. So here you can see that root locus can be defined as a graphical method in which we can sketch different values of s, separate different roots of s in when a particular variable is varied from 0 to infinity. Okay, so that's what I am saying here. So let's assume an example where we have gs is equals to, let's see, k upon s. Okay, so here the characteristic equation will be 1 plus with the unity feedback. Okay, so here the characteristic equation will be 1 plus GSHS is equals to 0, or here I will get S plus K is equals to 0. Okay, now solving here. So if I am varying K, then from 0 to infinity, let's say 0 to infinity. So what will be from here? S is equals to minus K. So I will get the values, separate value of s. When k is 0, then s is also 0. When k is 1, s is minus 1. K is 2, s is minus 2. K is 5, s is minus 5. And when k is infinity, s is minus infinity. So I can plot it on the s plane, the values of this s. This is the real part and this is the imaginary part of the characteristic equation. So here is 1 point, s is equals to 0, at minus 1, s is equals to minus 2, this s is equals to minus 3, up to so on till minus infinity, right? So when I am joining all these points, okay, the locus of all these points will give us the root locus, right? For separate values of k, I am getting separate values of s, that means separate set of roots of the characteristic equation, or you can say the roots, the closed loop poles, and the locus of when I am joining these all these poles, so the locus of all these roots is giving me the root locus. I hope this is clear. So in this case, for this example, the negative real axis is the whole negative real axis will be the root locus. Now coming to the angle and magnitude condition. See, we know the characteristic equation 1 plus GSHS is equals to 0. Okay, and if I write GS from here, I can write GSHS is equals to minus 1. Shall I write it minus 1 plus J0, right? So I can find out the angle with this. For this, the angle for GSHS can be written as tan inverse 0 upon minus 1. So what will be tan inverse 0? Can I write it plus minus k 180 degree? Why so? Because here this minus 1 is, if I plot it this point, then I'll get here minus 1. So I am writing here plus minus 180 degree just because of this point. So I can define angle condition as the angle of GSHS for different values of S when this is an odd when angle of GSHS is an odd multiple of 180 degree, because I want the angle at the negative real axis. So shall I write the angle of GSHS is equal to plus minus 2q plus 1 into 180 degree, because here I am getting 180 degree plus minus or 540, and otherwise we can say 900 degree up to so on. So in general I can conclude that the angle of GSHS will be plus minus 2q plus 1 into 180 degree, right? That is, the angle condition will be the angle of GSHS for values of S, right, in which the roots of the characteristic equation is then odd multiple of 180 degree. Okay. So the point of the points on the root locus branch will satisfy the angle condition. So basically this angle condition is used to know whether the point exists on the root locus branch or not. So we can find the value of k for the points on the root locus branches by using the magnitude condition, right? So we can use magnitude condition for the points which satisfy the angle condition. This is vice versa. So what is magnitude condition? It can also be obtained from the characteristic equation 1 plus, as we know that 1 plus GSHS is equals to 0, or shall I write it GSHS is equals to minus 1, right? When I am taking the magnitude of GSHS, then magnitude of GSHS will come to be 1, right? So this is the actually the magnitude of the characteristic equation, right? So we can say that the magnitude condition for the magnitude condition for different values of k on the root locus can be determined by using the magnitude condition, which is mode of GSHS is equals to 1. Now coming to the rules of the construction of the root locus, there are many rules for the construction of root locus. First point is we should know that the root locus is symmetrical about the real axis, okay, horizontal real axis, right? So first of all we have to locate open loop poles and open loop zeros in the S plane. Then second point is we have to find out the branches of the root locus. So using this we can find the root locus branches. If P is greater than Z, P is the open loop poles and Z is the open loop zero, and if P is greater than equal to Z, then the number of branches of the root locus will be equal to P, and if P is less than Z, that means Z is greater than P, the number of branches of root locus will be equal to Z, right, whichever is greater. Now third point is we have to identify and draw the root locus real axis root locus branches, right. So if the angle of the open loop transfer function is at a point is an odd multiple of 180 degree, right, then the point is on the root locus, which we have described here. This odd multiple of 180 degree means angle condition if it is satisfying, right, and then the point will be on the root locus. If the odd number of poles, open loop poles and zeros exist on the left side at a point on the real axis, then the point is on the root locus branch. So therefore we can say that the branches of the points, the branch of the root locus which satisfied the condition is the real axis of the root locus branch, right. Now fourth rule is we have to find out the centroid, right. So centroid will be if P is equals to Z, right. One point is missing here, that the branches of the root locus will always originate from open loop poles, right, and will always terminate open loop poles and will always terminate at either at open loop zeros or at infinity. This point is very important. Okay? Now fourth point is we have to find out the centroid as well as the angle of asymptotes. Right? See, these asymptotes are the guidelines for the branches of the root locus. They guide the branch of the root locus in which direction the branches of the root locus have to move. Right? And asymptotes can be plotted from a point that is known as centroid. Right? So the formula for the asymptote will be the formula for the asymptote, it is represented by theta or phi, and the formula will be 2q plus 1 into 180 degree upon p minus z, where this q will vary from 0 to 1 to up to p minus z minus 1. Okay, and this is the formula for the centroid. Now these asymptotes will always be represented by dotted lines in any particular graph, right? And by using this formula we can find out the asymptotes for any graph, and now these asymptotes are always plotted from the centroid, right? Centroid is a point which from which the we can plot the asymptotes on the root locus graph, right? So the formula for the centroid is it is represented by alpha or sigma, and the formula is the summation of real part of finite open loop poles minus summation of real part of finite open loop zeros upon p minus z. Okay, so here you can see one point is, if p is equals to z, then all the roots of the branches will originate or start from the open loop poles and end at finite open loop zero. In the previous slide I have told you that all the branches of the root locus will originate from the open loop poles, right, and terminate either towards that 0 or towards that infinity. So this is the description for that, ki all the branches will definitely started or originated from open loop poles, but if p is equals to z, then in that case all the branches will terminate at open loop 0, but if p is greater than z, then the p minus z number of branches will end at p minus z branches will end at infinite, and z number of branches will end at zeros, right? And if p is less than z, then the number of root locus branches will definitely started from the open loop poles but end at finite number of open loop zeros, and z minus k p number of branches of the root locus will start at infinite open loop poles and end at finite open loop zeros. Okay, so this is the formula for centroid. Now here they have given, I have written the formula for asymptotes, right? Now the fifth point is the intersection with the imaginary axis, right? So how to calculate the intersection with the imaginary axis? So intersection of the root locus points with the imaginary axis can be determined by using the Routh-Hurwitz criteria, right? There we have 3 points. When we calculate the point at which the root locus branches intersect at the imaginary axis and the value of k at that point by using the Routh-Hurwitz method. See, so this is the special case 2. In the Routh-Hurwitz method we have studied the 2 special cases. One is when a single element is 0, when a single element in a column in a row is 0, and second case, special case, is when all the elements in a row is 0. So this is case 2 in which all the elements of a row are 0. So we have to always apply this special case 2 of the Routh-Hurwitz criteria to determine the intersection point of the branches of the root locus with the imaginary axis. See, if so what is the procedure? If all the elements of any row of the Routh-Hurwitz are 0, Routh array are 0, then the root locus branches intersect the imaginary axis and vice versa, right? So what we have to do is, you have to first identify the row in which all the elements are 0, right? Then what you have to do is, you have to find the value of k for that particular combination. How we can find out the value of k? We will consider the first column only, right? We know for stability purpose, the first all the elements of the first column must be greater than 0. That means all the elements of the first column will be positive, right? So in that case, whatever be the elements in the first column, we will put them in which the k is there present, right? So we'll take that particular element and keep it greater than 0, right? Like for example, if it is 6 minus k upon 2, then I'll take this element from the first column and put it equals to greater than 0, this term. Then I'll get the value of the k from this term, which is the marginal value of k. And if I put this marginal value of k in that particular row, then I'll get in the row which is above the row in which the elements are 0, right? So that row will be the row will be called as the auxiliary equation, auxiliary row, and we can write down the auxiliary equation using that row, right? And from that auxiliary equation, when I substitute the value of k, right, I'll get the points which are cutting the intersection points of the branches of the root locus with the imaginary axis. Okay. Now rule number 6, we have to find out the breakaway and break-in points. Since when there are two consecutive open loop poles, right, then there will be a breakaway point, and when they are consecutive to open loop zeros, then definitely there will be a break-in point. Now how to find out this breakaway point and how to find out this break-in point? So we know the this can be find out with the help of the characteristic equation, okay, which is 1 plus GSHS is equals to 0. So first of all, we'll find out the characteristic equation, then we'll see here 1 plus GSHS is equals to 0. Then from here I'll convert this equation in terms of k, okay. Then I'll take dk by ds is equals to 0. Then differentiate this k with respect to s and keep it equal to 0. From here I'll get the values of different values of s, that means roots of s. Now those roots can be put in this again in this equation, right, and the value for the root of s for which this k is positive will be called as the valid breakaway point, okay. And for break-in point, we have to double differentiate the value of k, right? That means for break-in point, we have to find out dk2 by d2k by ds2, and which should be greater than 0. From here we'll get the break-in point, and it is the case when we have two consecutive zeros, and for two consecutive poles we always have to find out the breakaway point. Why? Because when two consecutive poles are there, then the two branches of the root locus are originating from those poles. Now we have to use the breakaway point to break them and going away from each other, right? And similarly for break-in point, when there are two consecutive zeros are there, then we have to use the break-in point, because the two branches are terminating at these two the two different branches are terminating at the consecutive zeros. So break-in point will converge these two branches and forward it to one branch, okay. Now the 7th point is we have to find out the angle of departure and the angle of arrival. So this point, these are the basically two different points. Point number 7 is to find out the angle of departure, and this is rule number 8, which is angle of arrival. angle of arrival. So these are used when there are complex poles and complex zeros in the equations in the system, right? So angle of departure is used in case of complex poles, right? And angle of arrival is used in case of complex zeros, right? So how this angle of departure, complex conjugate poles and zeros, right? How this angle of departure and arrival can be calculated. So this is the formula for the angle of departure, which is 180 degree minus phi, and this phi is the summation of poles minus summation of zeros. Now what is the summation of poles? So this summation of poles is contribution made by the other angles to the complex conjugate pole, right? And this summation of phi z will be the contribution of all the angles made by open loop zeros at that complex conjugate pole at which phi d is to be calculated, and this is by the other remaining poles at that complex conjugate pole, right? And angle of arrival is, it's just this reverse. This will be 180 degree plus phi, and the phi is same, that is phi p minus phi z. This is the contribution of all other open loop poles to this particular zero, right? And at which we have to find out the angle of arrival, and this is contribution of all other open loop zeros at this complex zero at which phi d is to phi a is to be calculated. Now I hope that it is the steps are clear. Now by using this example I am able to explain it more clearly. So this is for unity feedback system. We have GS is equals to, here GS is equals to K upon S into S plus 4 into S plus 2, right? So we have to sketch the root locus for this value of S, right? And we have to comment on the stability of the system. So first step here is to find out the number of poles, the number of zeros, and the number of branches of the root locus. So here we have 3 poles which are located at S is equals to 0, S is equals to minus 4, and S is equals to minus 2. And here there is no 0 in this system. Okay. Now the number of branches will be equal to number of poles, as P is greater than Z. That means there are 3 branches of the root locus, right? Now all these 3 branches of the root locus will originate from open loop poles and terminates towards K is equals to infinity. Why so? Because there is no 0 in this system. Okay, I can plot here also. So this is S is equals to 0, let's say this is minus 2, and let's say this is minus 4. So S is equals to minus 2 and S is equals to minus 4. Okay. Now another thing that I can see here is to find the region of where root locus is lying. So for that purpose I'll select the point, let's say this point P, this is the point Q, and this is the point R. Okay, so let me use another pen. So for point R, if the number, I have to check in which region root locus is lying on this negative real axis, as I know that the root locus is symmetrical about the horizontal real axis. Okay, so see for this point R, right, if I see towards the right side, the total number, the sum of poles and zeros must be odd. If it is odd, then this region is the region of root locus, and if the number is even, then this region is not the this is the region in which root locus will not lie. Okay, so if I count here 1 2 3, I have 3 poles here, so that means this is the region where root locus can lie, यहाँ पे lie कर सकता है. So I can write it as RL, and if I see this point Q, so it's point Q के, when I'll see the right side, I have 2 poles here only. Okay, that means which is an even number. So in this region, root locus will not lie. Is I can write as not a root locus, NRL. Not root locus will not lie in between -2 and -4. And for if I take point P and C towards right, then I have only one pole, which is an odd number. So here also root locus lies. तो यहाँ पर भी रूट लोकस 0 से -2 में लाई करेगा, या फिर रूट लोकस हमारा -4 से -इंफिनिटी के रीजन में लाई करेगा, बट -2 से -4 के बीच में रूट लोकस हमारा लाई नहीं करेगा. ओके, सो हियर रीजन ऑफ रूट लोकस विल बी आइदर फ्रॉम 0 से -2, ओके, एंड और -4 से -इंफिनिटी. ठीक है. Now step 3 is to find out the number of asymptotes. So asymptotes can be calculated with the formula, that is 2q phi is equals to 2q plus 1 into 180 degree upon p minus z, and q will be here equal to 0 1 till p minus z minus 1. So here p minus z is 3 minus 0 minus 1, that means 2 na. So Q, I'll calculate, there will be 3 asymptotes for this system, phi 1, phi 2, phi 3, and I'll calculate it for 0, 1 and 2. Okay. So phi 1 will be when Q is equals to 0 here, then 180 upon P minus Z is 3, 180 upon 3 is 60 degree. And phi 2 will be Q is equals to 1, that means 2 into 1 plus 1, that is 3 into 180 degree upon 3. Okay, so it comes out to be 180 degree. And phi 3 will be 2q plus 1, that means if I put q is equals to 2, that means it comes out to be 5, 180 degree by 3. So this is 60 and this is 300 degree. Now these 3 angles will be plotted using the point that is called centroid. It is represented by sigma, which is the summation of real part of poles minus summation of real part of zeros, which is 0 here, upon p minus z. तो रियल पार्ट्स क्या है यहाँ पे पोल्स के? 0, -4 एंड -2. तो 0, -4 एंड -2, -0 तो है ही नहीं सिस्टम में, एंड p माइनस z इज हियर 3 है ना, 3 पोल्स है, 0 एक भी नहीं है, तो दैट इज -6/3 इज -2. तो इस सिस्टम में मैं यहाँ पर -2 से प्लॉट कर सकती हूँ 3 एंगल्स. -2 इज द पॉइंट फॉर द सेंट्रॉइड हियर. -2 पे सेंट्रॉइड लाई कर रहा है, और 3 एंगल क्या क्या है हमारे? एक है 60 डिग्री, दिस इज 60 डिग्री, देन हमारा कौन सा एंगल था? 180 एंड 300. तो दिस इज 180 डिग्री and 300 will be from here, this is will be the 300, this is 300. As I have told you that these asymptotes will be shown by the dotted lines, and these will show us, these will guide the branches of the root locus. Now you know there are the 3 branches of root locus. So the 3 branches will originate, one branches from 3 open loop poles, 1, 2 and 3. Now this branch will originate, since this is not the region of root locus, so this branch will originate from here and terminates towards here, towards k is equals to infinity, right? Now these 2 branches will since this is the region of root locus, so these are the 2 consecutive poles, so these branches will originate from these 2 poles of the root poles, and now they will, we have to find out the breakaway point so that they will meet at a point and break away from each other, right? Now what is the breakaway point that I have to find out? So next point is, let me find out the breakaway point here. So breakaway point can be calculated by using the characteristic equation, which is 1 plus GSHS is equals to 0. 1 plus GSHS is equals to 0. And for this system, this is k upon 1 plus k upon s into s plus 2 into s plus 4 equals to 0. So it comes out to be s into s plus 2 into s plus 4 is equals to plus k is equals to 0. So I want the equation in terms of s, which will be minus, I can directly write it is s cube plus 2 4 ja 8, that means 8s, and this is 6s, that means I can write it as 6s square. Okay, now I have to differentiate k with respect to s and put this equation equals to 0. So differentiation ke baad I'll get 3s square plus 12s plus 8, and now I'll keep equals to 0. So from here I'll get two values of s, which one is minus 0.845 and another one s2 is equals to minus 3.15. So what I have to do is putting the value of this s1 in this equation, putting value of s1 in equation, let's say this is equation 1, s1 in equation 1, I'll get k is equals to either positive or negative. Just I have to determine whether it is positive or negative. तो s1 जब हमने put किया तो k will be positive, and when I put value of s2 in equation 2, I'll get k is equals to negative. So s1 is the valid breakaway point. Since I am getting k as positive here, so s1 is the valid breakaway point. That means valid breakaway point. That means minus 0.845 is the valid breakaway point here, and this is neglected. So now those two branches which are originating from here, open loop poles 2 minus 2 and 0, and they'll meet at minus, what was that value, minus 8.845 minus 0.845, they'll meet at this point and they'll break away, and one branch will go towards here and another will go towards here. These asymptotes are assisting those branches. Now I have to find out these two branches and terminating towards k is equals to infinity. All the three branches here in this case will terminate towards infinity as z is equals to 0. Okay. Now I have to find out these 2 points at which these branches of root locus are intersecting the imaginary axis, right? So the intersection with imaginary axis, next point is that I have to find out the intersection with imaginary axis. Then this can be calculated, find out by using the Routh-Hurwitz criteria. So for Routh-Hurwitz criteria, again I'll write here using RH criteria, Routh-Hurwitz array. Okay. So for this again I need 1 plus GSHS is equals to 0, which is the characteristic equation, and which is this s into s plus 2 into s plus 4 plus k is equals to 0. If I solve it, then I'll get s cube plus, what I am getting, s cube plus 6s square plus 8s plus k is equals to 0. Now when I'll draw the Routh array, s cube plus s square, then s ki power 1 and then s ki power 0. From here I am getting 1, 8, and this is 6 and this is k, then this is 48, 6, 4, 8 ja 48 minus k upon 6, and यहाँ पे कुछ भी नहीं आएगा, this will be left blank, and then this into this minus this upon this will be k. So we'll see the first column here only, right? So the first column here, we'll look into the matter only. First column में all elements must be positive. That means 48 minus k upon 6 must be greater than 0 and k must be greater than 0. So this shows that k must be less than 48. Okay, that means k marginal will be equal to 48, and the range of k from here I'll get 0 to 48. Okay, this is the range of k that I am getting. Now k marginal is 48. If I put the value of k here, this is the case, special case 2, then all the elements of a row will become 0. So I'll consider the above equation, this equation, which can be said as the auxiliary equation, will be equals to here 6s square plus k, and value of k here is 48. So I'll put this value of k here in this equation, and when I'll equate it to 0, I'll get two values of s, as it is a quadratic equation, and those two values are, see here, this is s square plus 8 is equals to 0. So from here s 1 comma 2 will be equal to minus under the root of 8, sorry, minus 8 na, sorry, it will be minus root 8, which come out to be this. That means this is the point at which the root locus branches are cutting the imaginary axis, that is j 2.8. So this will be the point. This is 2.8 j, and as I know this is the imaginary axis, this is the real axis, and this is minus j 2.8. So for this, now this will be the final root locus for this system, which is having the unity feedback system, which is having this gain. So in this way you can draw the root locus of any given system, closed loop system. That's all for today's. Thank you so much.